So we're going to talk a little bit about work and energy in this chapter. And you're familiar with energy. It's what you put in your car. It's what you put in your body. Energy comes in a wide range of forms, and we're going to discuss some of them in this chapter. The reason energy is useful as a physical quantity like force and velocity and acceleration and so on is really because energy obeys what we call a conservation principle. The first law of thermodynamics, or so a variant of it, is that in an isolated system, the total energy is constant. And so if you have a system that you know is complete, then if something happens in it, you still know that the total energy is constant. And so a particle physicist would say something like this: if my system is the particle that I'm slamming into some object, and the object that's being slammed into, and I know the energy of those before they collide, then the energy afterwards is the same. And that means if I can account for all the particles after this collision, and I add up all their energies, I should get what I started with at the beginning. And it helps them find little missing parts, because if they add up all the energy and it doesn't add up to what they started with, then they're missing a particle. And so it helps them account for various things like that. It's used in the kind of physics we do in tracking the motion of objects, the velocities and accelerations and so on of different objects in a system. And so the only caveat to the conservation principle is that for relativistic collisions, which we won't deal with, energy can transfer back and forth to mass. And so the conservationist principle is still valid as long as you allow for the fact that occasionally some mass gets produced, and that's there instead of the energy. We're going to begin this chapter really with a discussion of work. And so work has a very specific definition, and it means something different to lay people than it does to physicists or scientists. But here's an operational definition of work: the work done on a system by a constant force. This is a force pushing on something, right? The work done on a system by a force is equal to the product of the component of the force in the direction of the motion times the distance through which the force acts. And so if we were to write this as an equation, I'll loop back up here to the top, we would write this way. This is our definition of work. It's the magnitude of the force times cosine of theta times the magnitude of the distance through which the force acts. And so, for example, if suppose I'm pushing a box like this, right? And my force is going this way, right? There's my force. But my box is going this way, right? Because it's along the floor, right? And so maybe my box moves a total distance like this, and we'll call that D, right? And there's my F. Then the work done is equal to the magnitude of the force times the cosine of the angle. And the angle is the angle between my D vector, which is, say, this guy. Technically, in this picture, the vector goes from here to here, right? Because that's how far it moved, that's the distance. And so my force vector, if I were to draw them off to the side, remember this isn't a free body diagram or anything, but here's my force direction and here's my distance direction. This would be called theta, right? And so if I were to make components of this force, it's the component of the force along the direction of the distance. This piece here is the magnitude of the force times the cosine of the angle between them. Try one more time. So if I break my force up into components, I might call this like F parallel, because it's the component of the force along the direction of motion. All right, so I'll do some examples of this in the next few slides, and hopefully you'll see from the examples what I mean. This guy should be a theta over there. I don't know if my writing is too messy. This is the magnitude of the force times the distance. Okay, so we'll go on from here. So here's a briefcase that's being carried upstairs, right? If the angle, so the briefcase is being pulled upward, but it's moving this way, right? And so if I want to find the work done, is the magnitude of the force times the cosine of the angle between the force and the distance times the magnitude of the distance, right? And so that's just the force times cosine theta times the distance. I leave the vectors off so that to tell you that I just mean the magnitude. And once again, I just have to take this, here's my theta here, right? That's theta. And I draw a perpendicular line here, and this is the component of the force. That thing is F cosine theta. It's the component of the force along the direction of the distance, right? Here's my distance vector. So we can talk a little bit about the work done by gravity, for example. So imagine I take a box, right, mass m, and I lift it a height d up here, right? Now, I'm exerting a force on it, but I'm not asking what work my force is doing. I'm asking what work gravity is doing. Remember, force of gravity points this way, right? And so if I want to say the work by gravity, that's equal to the magnitude of the force of gravity times the cosine of the angle, and this is the angle between the force of gravity and the distance, times the magnitude of the distance. Notice that the angle between the force of gravity and the distance is 180 degrees. Right? The force points this way, the distance points that way, and so that's equal to the force of gravity. The magnitude is just we just write it as the variable without the vector thing on top, times the cosine of 180 degrees times the distance. And that's equal to minus force of gravity times the distance, which is minus mass times gravity times the distance, right? This is the work by gravity. So notice that when the force is acting in opposite direction motion, the work done is negative. It would also be true if my distance is this way and my force is like that, right? Because then the component is opposite, right? And so if this is my distance and this is my force, then this is my force times cosine theta, and it points that way. And so I would have the cosine of that angle. This would be the angle of interest, right? The angle between the force and the distance. Cosine of anything over 90 degrees, between 90 degrees and 270 degrees, is negative. And so this number will come out negative. It will give me a negative work done. And so really when the force is kind of taking energy away, the work done is negative. When the force is putting energy in, the work is positive. And when they're perpendicular to each other, the force isn't adding or subtracting any energy from the system, and so the work done is zero. That's when the force and the distance are at 90 degrees. So Bob pushes a lawnmower with a force of 75 newtons at an angle of 35 degrees below the horizontal as it moves 25 meters on level ground, right? And so here's Bob. Here's the lawnmower. That's the sound the lawnmower makes, right? So he's pushing with a force this way, right, of F equals 75 newtons. The mower travels this way, 25 meters, right? And this angle that these two make is 35 degrees, right? And so we need to get the horizontal component, F cosine of theta, so that we're multiplying, right, the work is equal to the force times cosine of theta times the distance. And so it's 75 newtons times the cosine of 35 degrees times 25 meters. And so what I get for that is about 1536 Newton meters of work done. And this we call a joule. It's 1 joule. And these are the SI unit of energy. So in question B, we're going to say convert this to kilocalories. So a calorie is the English unit of energy, and so 1 kilocalorie equals 4186 joules. Sometimes you'll see 4180, sometimes you'll see 4184. There's some subtle differences about how that's calculated, but it doesn't matter. They're all within a fraction of a percent of each other, and so it's fine. Use any value. And so to get the work done in kilocalories, I take 1536 joules and multiply it by 1 kilocalorie. A kilocalorie, again, is a food calorie, and so sometimes you'll see kilocalorie equals 1 calorie with a capital C. Kilocalorie. And so over 4186, and that's that's 0.367 food calories. Maybe I'll go back up to the top then here. So well under 1% of his daily calories was pushing the lawnmower along the horizontal. Turns out a good fraction of the calories you burn in a day is just heating your body, keeping your body warm. So up until now, we were just talking about the work done by an individual force. So we said work equals the magnitude of the force times cosine of the angle between the force and the distance times the magnitude of the distance. So this is the work done by a force on some object, by a force F on some object that moves the distance d. But we can also say just W net, the net work done on a system, if we take up all the forces, is just the net force times cosine of theta times the magnitude of the distance, right? And this is when you just take the vector sum of all the forces, which may or may not be acting along the distance it moves, and then multiplying that by the cosine of the angle between them, right? It turns out you can draw a graph of this. You can graph F cosine theta, or F net cosine theta, either one, depending on what you're after, versus the distance. Right? And if this quantity is constant, that is, if the angle isn't changing and the force isn't changing, you get something like this. And if, this is D initial and this is D final, then the product of these two is just the area under this curve. Is the area in this case, it's really not a curve, it's a line, but you can also have, for example, a more general, right? Because this is just, the height of this thing is F cosine theta, and the width of this thing is just D, right? And so, but you can also have something more complicated than that. You can have the force, you can have F cosine theta is changing somehow, right? So it's not constant as the distance is changing. And so instead you get a more complicated picture. This is again the distance here. But you can treat each one of these, you can treat this as like a little so on. Right. You can treat this as a constant force over a smaller region, successively smaller regions, so that each one of these was just the work done in this rectangle was this F cosine theta times, this F cosine theta times that distance. In this block, the work done was this F cosine theta times that distance, and so on, and add them up. Well, if you take smaller and smaller rectangles, what you end up with is the area under this curve, again, just like the area under that curve, right? This here. So in a graph of F cosine theta versus distance, the area is the work done. We'll see that again.